forgotten to hit the record button, because if I had $1 for every time, I probably would not be teaching anymore. I'd be sipping on a pina colada somewhere on a paradise island. All right. Thank you for reminding me.
No problem.
Okay. Ladies and gentlemen, another thing that I want to draw your attention to here. How do we even know that f of x equals 2x minus 3 is a function? Does anybody remember a test you can subject the graph of a relation in mathematics to determine, whether or not it's a function? Anybody remember the name of that test? Anybody remember the name of the test you subject the graph of a relation to determine if it's a function or not? It's called the blank line test. Anybody remember that, the name of that test? The blank line test. What goes in the blank?
Vertical line test.
Yes, the vertical line test. Look at, if you take a hypothetical vertical line in the XY plane here, and if you sweep it from left to right or right to left, doesn't matter, that vertical line would only touch this red graph and at most 1 point anywhere. Because of that, f of x equals 2x minus 3, this relation is a special type of relation known as a function. Notice the inverse function is also, the inverse relation of our original relation is also a function. F inverse of x, the graph, which is the graph of this green line, also passes the vertical line test. It's also a function. Now, another thing that has to be evident that we will find out in the near future is that in order for a function to possess an inverse, ladies and gentlemen, not all functions have inverses. In order for a function to possess an inverse, a function also has to be a one-to-one function. What it means for a function to be one-to-one is it means for every output value the function maps to the range, that value has to come from one and only one value in the domain. Ladies and gentlemen, there is also an equally easy test to subject the graph of a function to see if it is a one-to-one function. It's called the horizontal line test. So if you look at the graph, this red line, the graph of f of x equals 2x minus 3, it is a one-to-one function, because if we take a horizontal line, and if we put the horizontal line anywhere in the xy plane, doesn't matter where you put it, that horizontal line would touch the red graph and at most 1 point. For that reason, we say that this linear function f of x equals 2x minus 3 is a one-to-one function. Because of that, it possesses an inverse. And its inverse function is f inverse of x, which is x plus 3 over 2. Notice the green line, the graph of the inverse function, also passes the horizontal line test. It's also a one-to-one function. It has to be, because its inverse is f of x equals 2x minus 3. Okay. All right, now, if we look at this next function, which is no longer a linear function, but it is called a quadratic function, y equals x squared minus 2, the graph of which would be a parabola opening upwards. The graph of this function, y equals x squared minus 2, would be this red parabolic graph that opens upwards, we say. The vertex point would be this minimum point down here at 0, -2. All right. Ladies and gentlemen, this red graph, this red parabola opening upwards definitely is a function, because a vertical line placed anywhere would only touch this red graph and at most 1 point. So it is a function, but I have a question for you. Is it a one-to-one function? Does this function, y equal x squared minus 2, does its graph pass the horizontal line test? And the answer is, what do you think? Yes or no? Anybody?
No.
Does not. Because if you take a horizontal line and put it through y equals 3, for example, the horizontal line would touch the graph in more than 1 point. Because of that, this function, y equals x squared minus 2, is not a one-to-one function, and therefore it would not possess an inverse function. Well, so what we are going to have to do is, we're going to see in the near future that we're going to have to restrict the domain of this quadratic function so as to force it to be a one-to-one function. But that aside, if we just try to find the inverse function of y equals x squared minus 2, ladies and gentlemen, we'll go through the same song and dance that we did on the linear function on the previous slide. We swap x and y, so x is equal to y squared minus 2. Then we solve the equation for y. But when we solve for y, we have to take the square root of both sides. And the problem is, ladies and gentlemen, when you take the square root of both sides here, okay, you have to include the plus or the minus square root. All right, the plus or minus. And the problem with graphing this inverse function now, which is plus or minus square root of x plus 2, which would be this green parabola opening to the right in the xy plane, is that this green parabola opening to the right, this relation in mathematics is not even a function because it fails to pass the vertical line test. And that's a big problem, all right? So what we would have to do with the domain of the original quadratic function y equals x squared minus 2 is restrict its domain to force it to be a one-to-one function so that its inverse will itself be a function and also be one-to-one. All right, we'll show you how to do that. All right, so this basically is alluding to what it means for a function to be a one-to-one function. We say a function is one-to-one if every element in the range comes from exactly one and only one element in the domain. In other words, you cannot have more than one element in the domain being mapped to the same element in the range by a function if it is to be one-to-one. And the horizontal line test helps you to correspond whether or determine whether a function is one-to-one. If a function y equals f of x is one-to-one, then the inverse function f is also a function that can be denoted by y equals f inverse of x. And ladies and gentlemen, the inverse function also then would be one-to-one. Right? Now we've seen this before, that f inverse does not represent the reciprocal of the function. That is, -1 does not imply that it's to be interpreted as an exponent. We interpret this as f inverse, not f to the -1 power. Okay. This is just showing us in general how we find the inverse of a function. We swap or interchange the roles of x and y in the equation. And then we solve the equation for y. Or we can take the graph of the original function and reflect it about the line y equals x to get the graph of the inverse function. Okay. All right, now trigonometric function, because that's really what this course is it's trigonometry. If I have my basic sine function here, and we graph, let's say 2 cycles of this thing. So I'm going to go to the left on the x-axis. So we got negative pi halves, negative pi, negative 3 pi halves, and then we got our negative 2 pi out here. So I'm just going to graph 2 cycles of y equals sine x, basic sine function. So we know that it starts at 0, 0. It maxes out at 1 at pi halves. Goes back to the x-axis at pi, mins out at 3 pi halves at -1, then comes back to the x-axis at 2 pi. It goes the other way too. It mins out at negative pi halves at -1, comes back to the x-axis at pi, maxes out at -3 pi half radians, which is -270 degrees, which is coterminal to pi halves, or 90 degrees. Comes back down to the x-axis at -2 pi, which is coterminal with 2 pi. All right. Now I'm going to draw this graph in a dash, using a dash curve. You'll see why in a second. So this is the graph of 2 cycles of y equals sine x. Okay, nothing new here. We've seen that before. The problem lays on with the graph of y equals sine x is that it is a function. The graph passes the vertical line test, but the graph does not pass the horizontal line test. Because if you put a horizontal line, let's say maybe down here, notice the horizontal line will touch the graph in more than one point. Okay, so the graph of y equals sine x on 2 cycles or 2 periods is not one-to-one. Because of that, ladies and gentlemen, in order to force this function to have an inverse, we have to force it to become a one-to-one function. And therefore, mathematicians have agreed or adopted, therefore, to restrict its domain to force it to be one-to-one. And they restrict the domain, ladies and gentlemen, to be between negative pi halves and positive pi halves. So therefore, the domain of the sine function is restricted to lie between negative pi halves, including negative pi halves, to positive pi halves. So this would be the interval notation that is used to represent the domain, the restricted domain, if you will, of the sine function to force it to be 1-to-1. So therefore, if we just allow the sine function's graph to be visible from negative pi halves to pi halves, now this function is 1-to-1 because its graph passes the horizontal line test. And therefore, the sine function now will possess an inverse function. Notice the range of this function is from negative 1-to-1, inclusive. Okay. All right. So if this is the graph of the sine function with its domain restricted, then, ladies and gentlemen, what would be the inverse function? Well, the inverse function, denoted as f inverse of x, is going to be the inverse sine function. Okay, the inverse sine function, or the inverse sine function is sometimes referred to as the arc sine function, arc sine. All righty. So I have a question for you. What would be the domain of this inverse trig function called the arc sine function? And what would be the range of this inverse function? What would be the domain of this inverse function? Anybody? What's the domain? This is the domain and range of the original function, sine x. What would be the domain of the inverse function called the inverse sine or the arc sine of x? What do you think it would be? Anybody? Remember what a function and its inverse do to the domain and range. Who can help me out here? Anthony, what do you think the domain of this inverse function would be if we know the domain and range of the original function, f of x equals sine x? Any clue? Trent, can you help us?
Would the domain and range be, would it be the opposite?
Yes, you're right. You are correct. It would be the opposite. So the domain of the arc sine function or the inverse sine function is going to be equal to the range of the original function, negative 1-to-1. And the range of the inverse function or the arc sine function is going to be the domain of the original function, which is from negative pi halves to pi halves, inclusive. That's exactly what's going to be the case here. So what do you think the graph of the arc sine function would look like? Well, ladies and gentlemen, I have the graph for us to look at. This, ladies and gentlemen, would be the graph of the arc sine function or the inverse sine function. Notice, as we just predicted, the domain is from negative 1 to positive 1. The range is from negative pi halves to positive pi halves. That's just the reverse of the sine function, domain and range. All right. So this is the graph of the sine, the inverse sine function or the arc sine function of x. Notice this relation passes the vertical line test, so it is a function. And the function rather passes the horizontal line test, so it's a 1-to-1 function. And it has to be 1-to-1 in order to possess an inverse. Okay. So this would be the graph of the arc sine function. Any questions about that there? So basically put, ladies and gentlemen, if you take the arc sine or the inverse sine of 1, you ask yourself, the sine of what angle gives you 1? The sine of what angle gives you 1 if you take the arc sine of 1? So if you take the arc sine of 1, ladies and gentlemen, that's saying the same thing as the sine of what angle would give you 1. And what angle would that have to be? The sine of what angle gives you positive 1? What quadrantal angle? That would be pi halves. Do you agree? Because the sine of pi halves is 1, so the arc sine of 1 must give you pi halves. So ladies and gentlemen, when you take the arc sine or the inverse sine of a number, you get back an angle. So when you take the arc sine or the inverse sine of a number, you get back an angle. When you take the sine of an angle, you get back a real number. Let me say that again, it's important. When you take the arc sine or inverse sine of a real number, you get back an angle. When you take the sine of an angle, you get back a real number. All right, just the opposite, they undo each other. All right. Okay, you can see that the arc sine of 0 is 0 because the arc sine of 0 is equal to what angle? Such that the sine of that angle would be 0. Well, the sine of 0 is 0. That's why the arc sine of 0 is 0. The arc sine of -1 would be what angle such that the sine of that angle would give you -1. Well, ladies and gentlemen, the sine of negative pi halves is -1. For that reason, the arc sine of -1 gives you the angle negative pi halves. Okay. Any questions how this inverse sine function is working and what its graph is saying here? All right. Well, in a similar fashion, ladies and gentlemen, if you think of the cosine function, it also is not 1-to-1. The cosine function, also its domain has to be restricted, ladies and gentlemen, in order to force it to be a 1-to-1 function. If you graph the basic cosine function on 2 periods, 0, pi halves, pi, 3 pi halves, 2 pi. Okay, we start at 0, up here at 1, go through the x-axis of pi halves. At pi, we're at -1. So I'm graphing y equals cosine x. 3 pi halves, we're back at the x-axis, and 2 pi, we max out at 1 again. So this would be the graph of one cycle of the cosine function. But ladies and gentlemen, notice this is not a 1-to-1 function because its graph fails the horizontal line test. If you put a horizontal line somewhere in the plane, like maybe right here, you can see a horizontal line would touch this graph in more than one point. Sorry about that. So therefore, this is not a 1-to-1 function, so it would not possess an inverse. To force this to be a 1-to-1 function, we have to restrict its domain. And so therefore, ladies and gentlemen, the domain of this function, f of x equals cosine x, the domain has to be restricted, and mathematicians choose to restrict the domain from x equals 0 to x equals pi. By restricting the domain from x equals 0 to pi, you can now see that the graph of the cosine function is 1-to-1. So the restricted domain of this cosine function would be from 0 to pi. The range of this cosine function is from -1 to 1. So the inverse function of the cosine function, denoted as inverse cosine of x, or ladies and gentlemen, it is referred to as the arc cosine function, arc cosine of x. What would be the domain of this inverse function called the arc cosine function now? Well, the domain of the arc cosine function of x is equal to the range of the cosine function of x, the range, and the range is from -1 to 1. So this would be the domain of the arc cosine function. The range of the arc cosine function is equal to the restricted domain of the cosine function, which is from 0 to pi. Okay. And so what would the graph of the arc cosine function look like on its domain from 0 to pi? Well, let's show you. This, ladies and gentlemen, would be the graph of the arc cosine function or the inverse cosine function. Notice its domain is from -1 to 1 and its range is from 0 to pi. So the arc cosine of -1, the arc cosine of -1 would give you some angle such that the cosine of that angle would have to be equal to -1. So ladies and gentlemen, think about it. The cosine of what angle gives you -1? Well, that would be pi. And for that reason, the arc cosine of -1 is pi. So the arc cosine of -1 is pi. You see that? Because the cosine of pi is -1. All right. What's the arc cosine of 0? The arc cosine of 0 is going to be some angle whose such that the cosine of that angle is 0. Well, the cosine of what angle is 0? Well, the cosine of pi halves radians is 0. So the arc cosine of 0 is equal to pi halves. Why? Because the cosine of pi halves is equal to 0. So the arc cosine of 0 is pi halves, because the cosine of pi halves is 0. Do we see how these things are working here a little bit, ladies and gentlemen? These inverse trig functions. That would be the graph of the arc cosine function. Okay. How about the tangent function? All right, if we graph the tangent function, ladies and gentlemen, f of x equals tangent x. We know that's the ratio of the sine of x divided by the cosine of x. This function will be undefined whenever the denominator is 0. In other words, it will be undefined for angles whose cosine is 0. Well, the cosine of what angles gives you 0? Well, that would be pi half radians. And that would also be what? 3 pi half radians. It's through these values we would have vertical asymptotes. And therefore, the graph of one cycle or one period of the cosine of the tangent function, rather, would be this guy right here, where the graph is asymptotic with respect to these vertical dashed lines called vertical asymptotes. This is 3 pi halves here. Okay. All right. And so if we continued onward here, if this is 5 pi half radians, the tangent would also be, the graph of the tangent function would be asymptotic with respect to 3 pi halves and also 5 pi halves. And we could go on forever graphing any number of cycles of this thing. But the problem, ladies and gentlemen, is this graph of this function tangent x is not 1-to-1, because a horizontal line placed somewhere in the xy plane would touch the graph in more than one point. And because of that, we like to restrict the domain of the tangent function. Now, if I went to the left, I would have negative pi halves as being another vertical asymptote over here. And this would be the graph of yet another cycle or period of the tangent function. And so, ladies and gentlemen, in order to force this function to be 1-to-1, we're going to have to do away with all cycles except one cycle. And mathematicians have adopted the restricted domain to be between negative pi halves and positive pi halves. So the domain of this tangent function is restricted, ladies and gentlemen, to be between negative pi halves and pi halves. But notice the tangent of negative pi halves is undefined. The tangent of pi halves is undefined. Because of that, the domain cannot actually contain these endpoints. So the interval notation for the domain, the restricted domain of the tangent function, would have to be this open interval here, from negative pi halves to pi halves, not including the endpoints. What would be the range of the tangent function? What's the range of this function, ladies and gentlemen? The range. Anybody? Range.
Negative infinity to infinity.
Yeah, negative infinity to positive infinity. That'd be the range. Okay, so now, therefore, the inverse function of the tangent function is called the inverse, is called the inverse tangent function, denoted this way symbolically, or, ladies and gentlemen, the inverse function of the tangent function is known as the arctan function, the arctangent function. And its domain would be equal to the range of the original function, the tangent function. So the domain of the inverse function, the arctangent function, would be from negative infinity to positive infinity. And the range of the arctangent function would be equal to the domain of the tangent function, which would be from negative pi halves to pi halves, not including these endpoints here. Okay. So what would the graph of the inverse tangent or the arctangent function look like? Well, I got a picture of that. Let's see. Here we go, ladies and gentlemen. This would be the graph of the arctangent function, which is the inverse tangent function. Notice its domain is from negative infinity to positive infinity. Negative infinity to positive infinity is the domain. The range is from negative pi halves to pi halves, not including those values. Hence we have, so the vertical asymptotes of tangent x become horizontal asymptotes of the graph of the arctangent of x. Notice that. Okay. That's the graph of the arctangent function. All right. Okay, so I just wanted to go over the inverse trig functions of the sine, cosine, and tangent. And of course, the other ones have inverses too, the inverse cosecant, secant, inverse cotangent. But the main ones I wanted to focus on would be those right there. Those are the ones that are usually encountered the most, ladies and gentlemen, in calculus, is the arc sine, arc cosine, arc tangent functions there. Okay. All right, so now that we know what those graphs look like, let's go back to our textbook here, and let's have a little bit of fun here. Notice you can see, before I get rid of this PowerPoint presentation here, you can see that we have the graph of the sine function, y equals sine x, and we also have the graph of the arc sine function, the red graph. You can see, ladies and gentlemen, how those graphs are symmetric with respect to this line y equals x. And that's evident with the graphs of any function and its inverse. They're always symmetric with respect to this line y equals x. It's kind of like, so if you fold this picture about this line y equals x, this blue branch of the sine x graph would mesh up with this red branch of the arc sine x. That's to say we have symmetry there. Okay. All right, so let's end this and try to get into our textbook here. All right, section 4.6. Let's see if we can do maybe a couple of problems here. As always, you're welcome to look at you know, the sections that I go over in your textbook. I encourage you to do that. By the way, ladies and gentlemen, I never did indicate what we would restrict our domain of our quadratic function y equals x squared minus 2 to be in order to force it to be a one-to-one function. Does anybody know what restricted domain we would have to go with y equals x squared minus 2 to force it to be a one-to-one function? It's kind of a challenging question. Anybody want to take a stab at that? What would we have to restrict the domain of y equals x squared minus 2 to in order for it to be a one-to-one function? I'll tell you what.
Well, X is all real values, right? Because it passes the vertical line test. So
Yes.
then it come down to the horizontal line test. So I would probably just chop it off at 0
Yeah,
and
exactly.
then just take either the negative or the positive.
Yeah, exactly. Yeah, all you got to do here, ladies and gentlemen, is just get rid of one of these branches here of this red parabolic graph. So normally it has been adopted that normally we like to get rid of the left branch. And so we like to restrict the domain of this quadratic function, y equals x squared minus 2, to be from 0 to positive infinity. And when you restrict the domain to be from 0 to positive infinity for y equals x squared minus 2, then you're going to be looking at this graph right here. And now, ladies and gentlemen, with this restricted domain from 0 to infinity, okay, this is now a one-to-one function. You agree? Because this graph passes the horizontal line test. All right. And therefore, if you were to graph the inverse function of this quadratic function, its graph is going to have to be, let's see here. If you start at positive 2, its graph would have to be this guy right here. Or let me see, let me make sure we got that here. So again, if you interchange X and Y here and then solve for Y, you get Y is equal to plus or minus the square root of X plus 2, correct? X plus 2. But we would go with the positive version of the square root here. So the square root of X plus 2, no, what it would be, ladies and gentlemen, it's not this graph right here, my bad. It would be this graph up here. Okay, that would be the graph of the inverse function, which is this quadratic function, this radical function, positive square root of X plus 2. That would be the inverse of that function there. And you can see that this function is also 1-to-1. A horizontal line would only touch the graph and at most 1 point anywhere either, because this is slowly but surely constantly rising here, this graph. Okay. So therefore, we would have to restrict the domain of our quadratic function to be from 0 to positive infinity in order for these graphs to possess an inverse here. And the graph of the inverse function would be, it would start here at -2 and it would go to the right. So the graph of the inverse function of the red parabola, when we restrict this domain, would be the upper branch of the green parabolic graph, just the upper branch, as we would do away with the lower branch. All right. And you can see then that the graph of the right red branch and the green upper branch definitely are symmetric with respect to this line y equals x here. Those would be inverses of each other. Okay, let's go down here. We'll see our problems here. The problems we'll be confronted with. These are just some problems where they want you to find the inverse of like algebraic relationships. Polynomial functions, although you do have a couple of exponential functions in 9 and 10 where they want you to find the inverse. That's pretty much algebra though. I want to try to concentrate on the trigonometry here. Okay, so what we need to understand, we need to try to remember here is something very important. What you need to know with these inverse trig functions here is we need to understand what the ranges of these inverse trig functions have to be. And so therefore, this table here is pretty important to if you're going to go into calculus, especially the second semester calculus, you want to be conscious of the ranges of these inverse trig functions. In other words, the range of the arc sine function or the inverse sine function is from negative pi halves to pi halves. Notice 0 would be included in there. What quadrants does that constitute to say from negative pi halves to pi halves? What quadrants in the XY plane would it be? Well, negative pi halves is down here. Pi halves is up here. Okay, so from negative pi halves to pi halves, ladies and gentlemen, that would encompass quadrants, what, number 4 and number 1. Everybody see that there? From negative pi halves to pi halves. And notice you have to pass through 0. So 0 obviously is in this closed interval here. Makes sense. 0 has to be halfway in between these values, correct? Okay. All right. The inverse cosine or the arc cosine, what's its range? Its range is from 0 to pi, and 0 to pi encompasses quadrants 1 and 2. The range of the inverse tangent or the arc tangent function is from negative pi halves to pi halves, not including those values. So those angles would be found in quadrants 1 and 4. These are the ranges of the inverse cotangent or the arc cotangent, the arc secant, the arc cosecant. These are the ranges. These are encountered a little less frequently in higher level math as opposed to the sine, cosine, and tangent inverses. That's why I kind of went over those in particular. But notice the range of the cotangent function does not consist of 0 or pi, and the range of the arc secant function does not consist of pi halves or pi halves, and the range of the arc cosecant function does not consist of 0. Okay, why doesn't the arc secant function's range consist of pi halves? Well, because can you take the secant of any angle, ladies and gentlemen, and get pi, the secant, if you take the secant of pi half radians, the secant of pi half radians is 1 over cosine of pi halves, but cosine pi halves is 0, and 1 divided by 0 is undefined. And that's why the arc secant of pi halves does not exist, because the secant of pi halves does not exist. Okay. All right, so yeah, it is wise to just kind of know these ranges, especially for the arc sine, arc cosine, and the arc tangent functions there. All right, well, let's see if we can do a couple problems here from our textbook. All right, so problem number 20, what would be the inverse cosine or the arc cosine of 1/2? And ladies and gentlemen, you know, if you don't have these memorized, you can, you know, always revert back to your unit circle. So we're looking for the arc cosine of 1/2. Okay, the arc cosine of 1/2 is going to give you some angle theta, such that, ladies and gentlemen, if you take the cosine of that angle theta, you better get 1/2. Now, what angle would that have to be? The cosine of one angle has to give you 1/2. Now, keep in mind, the range of the arc cosine function is from what to what? It's from 0 to pi. So your angle has to be an angle between 0 and pi inclusive. So the cosine of what angle between 0 and pi gives you 1/2. Anybody? And notice this is a positive 1/2. And the range encompasses quadrants, what, 1 and 2 for the arc cosine function. So what quadrant would we be talking about if the cosine of this angle theta has to be positive 1/2? Would that be quadrant 1 or 2? What do you think? Quadrant 1 or 2?
Quadrant 1.
Quadrant 1. Yeah, it has to be a first quadrant angle because the cosine of that first quadrant angle has to give you a positive 1/2. The cosine of second quadrant angles is always negative. So our angle, our answer to the arc cosine of 1/2 has to be a positive angle that lies in quadrant 1. And anybody know what angle that would be? The cosine of what radian measurement in quadrant 1 gives you 1/2?
Is it 60?
60 degrees. What would that be in radians? 60 degrees is pi what?
Pi thirds.
Pi thirds. So the arc cosine, ladies and gentlemen, or the inverse cosine of 1/2 is pi third radians. That would be your answer. And notice this does come from quadrant number 1, which is a legitimate quadrant for the range values of the arc cosine function. All right, let's try another one here. Let's see. Okay, number 27, the inverse sine of negative 1/2. The inverse sine of negative 1/2 is really saying, what is the arc sine of negative 1/2? So what would be the arc sine of negative 1/2? Well, it's going to be some angle such that if you were to take the sine of that angle, you would get back negative 1/2. Think of it that way, okay? What is the range of the arc sine function? The range of the arc sine function is, do we remember? See, it comes back to that table. That table is also in section 4.6 in your textbook that gives you the ranges. The ranges of the inverse sine function or the arc sine function, recall, is from negative pi halves to pi halves. That's the range, which constitutes quadrants numbers 1 and 4. So ladies, I'm going to think about it. What quadrant would our angle have to come from if the sine of that angle is a negative 1/2? Quadrant 1 or 4?
4.
4. Has to be a fourth quadrant angle because the sine of that angle has to be a negative 1/2. And we're restricted to choosing between quadrants 1 and 2. So it has to be quadrant 4. So the sine of what fourth quadrant angle gives you negative 1/2? Anybody? The sine of what angle gives you negative 1/2? just let me ask you this question here. The sine of what angle in general, any angle, the sine of what angle gives you one half negative, just gives you one half. The
30?
sine- What's that?
It would be 30, but if
30
it's in the
degrees.
fourth quadrant, does that mean it would have to be like 330, sine of 330?
Okay, but notice 330 degrees does not lie between negative 90 degrees and 90 degrees. Okay, so instead of saying 330 degrees, we're going to use the angle negative pi sixth. Okay, negative pi six. So ladies and gentlemen, our answer is negative pi six here for the arc sine of negative one half. Because notice negative pi six does lie in this interval. It does lie between negative pi halves and pi halves. Think of the real number line here. Here's negative pi halves. Here's negative pi halves, and here's pi halves. And of course, zero is in between here. So this constitutes the what? The fourth quadrant angles, albeit the angles are negative. And this constitutes the first quadrant angles. Negative pi six would lie somewhere in here. So it's definitely in that interval. Okay. So the arc sine of negative one half is negative pi six. All righty. And you know, we know that 330 degrees would be coterminal with negative 30 degrees. Don't get me wrong. But if we are to adhere to the strict range of the arc cosine, the arc sine function, we can only use the angle negative pi six for the answer, that answer. That's why you need to kind of be conscious of the ranges of these inverse trig functions if you're going to get these problems correct here. Okay. All right, now these problems here, 39 to 52, they want you to use your calculator to evaluate each expression to the nearest tenth of a degree. And so we will have to dig up our machine, and I am going to go get my calculator here. So let's bring our calculator up and show ourselves how to do a problem or two out of here. All right. Okay, so here we go. All right, so let's bring up the calculator. And let's try a problem out here. All right, let's try number 40 here. They want you to evaluate the inverse sine or the arc sine of negative 0.1702. Got a question for you, ladies and gentlemen. All the arguments of these inverse trig functions, are they real numbers or are they angles? Anybody? Are these real numbers or are these angles, all these decimals here? When you take the inverse sine or the inverse cosine or the inverse tangent of a value, is that value an angle or a real number?
An angle.
It's an angle? So you're saying all of these decimals are angles?
Never mind, not an angle.
Yeah, they're not angles, ladies and gentlemen, they're just real numbers. Remember, when you take an inverse trig function of a real number, you get back an angle. So the answers to all these problems are going to be angles, because you're taking an inverse trig function of a real number. Okay. All right, so let's try number 40. The inverse sine of negative 0.1702 would be what angle theta? Well, to help you to better understand what your answer has to be, I think it's wise to, whenever you're looking at an inverse trig function of a real number value, I think it's wise, ladies and gentlemen, to understand what it's really implying about the original function or the other function. For instance, the inverse sine of negative 0.1702 is really saying it's going to, okay, this is going to give you some sort of an angle theta, such that if you take the sine of that angle theta, you better get back this decimal, negative 0.1702. That's how you want to think about it, okay? What's the range of the inverse sine function? Do we recall? Well, ladies and gentlemen, it's from negative pi halves to pi halves. That's the range. So our answer theta here, okay, our answer theta that we're going to get for this problem here better be an angle that lies in between negative pi halves and pi half radians. Has to be. Furthermore, ladies and gentlemen, notice that this range is in quadrants what? 1 and 4. So I have a question for you. what quadrant is our angle going to be found in, 1 or 4? If the sine of the angle is to be a negative ratio, what quadrant does it have to be? It has to be down here in what, quadrant 4, because the sine of a first quadrant angle is a positive, not a negative. So it's going to be a fourth quadrant angle, albeit it will be a negative angle because it has to be in this range interval for the arcsine function. All right, so get on your calculator and take the inverse sine of this decimal. Oh, you might want to make sure your calculator's in what, radian mode. I'll tell you what, ladies and gentlemen, let's put our calculator in degree mode first. Let's put our calculator in degree mode. Let's take the inverse sine, so second sine button of that decimal, which is negative 0.1702. And what do we get? Well, notice we get a negative angle, which is in the fourth quadrant, negative 9.799 degrees. But they want your answer, well, they do want it in the nearest tenth of a degree. So we have to put our calculator in degree mode. I thought they wanted the answers in radians. So what would be our answer? Our answer would be negative 9.8 degrees. And there you go, ladies and gentlemen, there's your answer, negative 9.8 degrees. Let's check our answer. Take the sine of negative 9.8 degrees. Do you get back that decimal that we had for the argument of the arcsine function? Notice you do get back negative 0.1702, blah, blah, blah. So the answer to question number 40 is negative 9.8 degrees. All right. That one make any sense there? Okay. Problem number, let's try number 50. The arctangent of negative 0.3640 would be what angle? Well, again, to say we're going to take the arctangent of some real number called negative 0.3640, that's going to give us some angle called theta back. But ladies and gentlemen, if you take the tangent of that angle theta, then you better get back to negative 0.3640. We know that the range of the arctangent function is in what quadrants? The range of the arctangent. Okay, so we know the range of the arctangent function has to be from negative pi halves to pi halves, but not including these values. So we're looking for an angle that lies in either quadrants 1 or 4, such that when you take the tangent of that angle, you get a negative. So what quadrant does our answer have to come from, quadrant 1 or 4, if the tangent is a negative ratio value, not a positive one? Well,
Fourth quadrant.
yeah, it's got to be the fourth quadrant. It can't be the first quadrant. The tangent of a first quadrant angle is positive. So it has to be the tangent of a fourth quadrant angle. And so keep that in mind. Our angle theta must be in the fourth quadrant. So let's take the arctangent of that decimal in your calculator. Go ahead and do that. What do you get? So let's take the arctangent of negative 0.3640. And when you do that, you get an angle. So your answer to this question would be negative 20.0 degrees. They wanted your answer rounded off to tenths. Negative 20.0 degrees. That would be your answer. So we understand how we're doing those problems here, ladies and gentlemen. Again, you have to be conscious of the range of these inverse trig functions if you are to get the correct angle. Because just because you take like an inverse sine, cosine, or tangent on your calculator, you may not get the correct answer, or the answer that we should be reporting. We might be getting like maybe a reference angle or something like that, okay? So you need to understand the range of the inverse sine, cosine, and inverse tangent function. All right. Okay, let's move down to these where they start getting a little heavier here, 53 through 68. They want you to evaluate without using a calculator. What does that mean? Well, that means we have to go cold turkey on this one here. We have to get rid of our lifeline, which is our calculator, and evaluate some of these here. All right, I'm going to do one like 54 here. They want us to evaluate the cosecant of the inverse tangent of 3/4. How are we going to do that? They don't want us to use any calculator either. No calculator. Are you serious? No calculator. That's what it says. Huh. Let's make sure I got the problem written down correctly. Yeah, looks like it. Without using a calculator. Okay, well, here we go. Ladies and gentlemen, we go inside the parentheses of the cosecant function, and we see that its argument is the inverse tangent of 3/4. The argument of the cosecant function is the inverse tangent or the arctangent of 3/4. So what does that mean? Well, first of all, we have to look at the argument. When we take the inverse tangent of 3/4, ladies and gentlemen, we are going to get back some angle theta. Do you agree? Do we all buy that, ladies and gentlemen? The inverse tangent of 3/4 is going to give us some sort of an angle theta. Remember, when you take the arctangent or inverse tangent of a real number, you get back an angle. If you take the tangent of an angle, you get back a real number. So if the arctangent or the inverse tangent of 3/4 is theta, this would therefore imply then that the tangent of that angle theta would have to give you back 3/4. Isn't that true? Well, now we can use this fact, ladies and gentlemen, to build ourselves a right triangle. Let's just build a right triangle here. Notice I'm not putting it in the XY plane. I'm just drawing a right triangle. I'll call this angle theta. Help me out, ladies and gentlemen. Help me label these sides now. If the tangent of this angle theta is 3/4, how do we label our sides? Remember, tangent is the ratio of what? So
Opposite over adjacent.
TOA, you are correct. Tangent, opposite over adjacent. So opposite over adjacent. Therefore, this side has to be opposite side 3. The adjacent side is 4. And then we can use the Pythagorean theorem to find the hypotenuse length.
5.
Yeah, and therefore you'll see that C is equal to the square root of 3 squared plus 4 squared. C is equal to the square root of 25, which is 5. You are correct. So this side would have to be 5. So your 3, 4, 5 triangle is a popular right triangle. All right, so what have we accomplished here? Well, ladies and gentlemen, I'm letting theta be equal to the inverse tangent of 3/4. Everybody see that right here? That's the first thing I said here. Well, that being the case, I could come back up to my original expression into my problem. I can replace the argument of the cosecant function with theta. So this is like saying we're taking the cosecant of theta. Because theta, again, is the inverse tangent of 3/4. So in place of this, I substitute in theta. But ladies and gentlemen, we already built our right triangle. So we're in business now, because the cosecant of theta now is going to be the ratio of the what? The hypotenuse. No, how does it work? Yeah, the inverse, the cosecant of theta will be the ratio of the hypotenuse over the opposite side. It's the reciprocal of the sine function. So therefore, the cosecant of theta will be 5/3, and we're done with this problem. Your answer is 5/3. So the cosecant of the inverse tangent of 3/4 is 5/3. Everybody understand how we just did that problem? The answer is 5/3. Okay, maybe we can try another one like that. Okay. Maybe we can try another one. All right, let's try another one. Do you want to pick one out of this batch here, ladies and gentlemen? 53 through 68, or What do you think the answer? Let me tell you this here. What do you think the answer to number 63 is going to be? What's the sign of the inverse sine of 3/5? Anybody? It's trivial. What's the answer?
Would it just be 5/3?
No, the answer is just literally what? 3/5.
Oh, 3/5.
3/5. The answer is 3/5. Look at, think of it this way. The sine and inverse sine functions undo each other. They basically annihilate each other. So just kind of like erase the sine and inverse sine function. You're left with 3/5. Your answer is 3/5. Answer to number 67. What's the tangent of the inverse tangent of 1/2? Answer is number 67.
1/2.
The answer is just
1/2.
1/2. The answer is 1/2. Answer to number 64. 3/5. Okay, so some of these are very simple here. The answer to number 66. 1 over the square root of 2. The answer to number 68. 3/4. Okay. So like I said, some of these are pretty simple. Maybe try another one out of here, or how about like number 58? That looks kind of complicated. What's the sine of the inverse cosine of 1 over the square root of 5? Well, we'll do this problem essentially the same way as I walked through the last one. When you take the inverse cosine of 1 over the square root of 5, you're going to get back an angle. So in order to evaluate this problem here, what we do is we're going to let theta be equal to the argument of the sine function. Let theta be equal to the inverse cosine of 1 over the square root of 5. Well, therefore, then that implies then that the cosine of this angle theta has to give you 1 over the square root of 5. Well, if that's true, then we can build a right triangle here. Call this theta. So therefore, the cosine of theta, being the ratio of the adjacent to the hypotenuse, would have to be 1 here, and this is a square root of 5. Now we can find the side y here. Pythagorean theorem. So y is going to be the square root of the hypotenuse squared minus the leg of 1 squared. So y is going to be the square root of 5 minus 1, or the square root of 4, or 2. So this side would have to be linked 2. So as I'm the sine of this inverse cosine of 1 over a square root of 5 is really like taking the sine of angle theta now, because theta is another name for the inverse cosine of 1 over the square root of 5. Well, what's the sine of theta? Well, we turn our attention to our right triangle we built. The sine of theta is a ratio of the opposite side to the hypotenuse. So the answer would be 2 over the square root of 5. Or after rationalizing the denominator, it would be 2 root 5 over 5. Okay. And there's your answer for number 58. Do we see how we're negotiating these problems here? This procedure that I am demonstrating for problems 54 and 58, you will revisit this procedure when you get into Calculus 2 and you look at a integration technique called trigonometric substitution. Okay, you'll revisit this. Okay, so that is that. So, ladies and gentlemen, I'm going to see if you can maybe do a problem or two for your classwork to wrap up this week. So today is what day? You know, sometimes I feel like I'm in the middle of the Pacific Ocean, like that movie Castaway. Have you ever seen that movie Castaway starring Tom Hanks? Anybody?
Yes, sir.
It feels like I'm on that raft in the middle of the Pacific Ocean. Sometimes I lose track of time and days and all that stuff, you know. All right, so class work for July, is it the 30th, 29th? 29th. It is the 29th. Okay. Hard to believe. It's just amazing how fast July went by. Oops, hold on a second. Let me switch to the view. So problem number 1 for our classwork today. Ladies and gentlemen, I would like you to try to evaluate a problem or two if possible. Problem number 1 here. I want you to try to evaluate what the arc sine of negative square root of 2/2 is going to be. Okay, that's problem number 1. Problem number 2. Oh, no calculator. No calculator for that problem. Problem number 2. I want you to do, I want you to find this angle. Theta is the the inverse cosine of negative 0.1334816. Okay, round to the nearest tenth of a degree. The angle, nearest tenth of degree. Problem number 3. All right, and then I want you to try this one without using a calculator. I want you to try to evaluate the cosine of the arc tangent of 8/3 without calculator. Okay. All right, so we'll call that classwork for today. Okay, see if you can do something with those problems, ladies and gentlemen. I have to convert it into an MP4 file, and that does take, seriously, on my computer, like, it takes about a half hour, 30 minutes. I know that's an unbelievable amount of time in this day and age, but I'm dealing with a stupid Commodore 64 computer here. So I will post a chapter 4 quiz, and it will be due by midnight Saturday night. Okay, so that'll give you a little bit, more time to, maybe take care of some other things in your life and all that. But midnight Saturday night, if you can get your chapter 4 quiz to me, and I will try like heck to get those chapter 3 exams finished off and graded. Okay, number 1, does anybody have an angle? The arc sine of negative square root of 2/2 is what angle? Anybody want to weigh in on that? Feeling confident? Anybody get an answer?
I got an answer. I'm not sure if it's right, but I got an answer.
Go ahead, what'd you get?
All right, my final answer was negative 45 degrees.
Okay, negative 45 degrees. In radians, what would that be?
Radians, that would be, let me,
Because the range of the arcsine functions from negative pi half to pi half radians. So
yeah, that would be negative negative pi over 4.
Okay, exactly. Here we go, ladies and gentlemen. Answer should be negative pi fourths. The arc sine of negative square root of 2 over 2 gives us an angle theta such that when you take the sine of an angle theta, you better get back negative square root of 2 over 2. The range of the arc sine function is from negative pi halves to pi halves. So the angle has to come from quadrant 1 or 4. Well, since the sine of that angle is a negative ratio, it has to come from quadrant 4. So it has to be negative pi fourths. That is correct. For problem number 2 here, the arc cosine or inverse cosine of this decimal would be such that the cosine of that angle theta would have to be equal to that decimal. The range of the inverse cosine function is from 0 to pi, which constitutes quadrants 1 and 2. Knowing that our cosine of that angle is a negative ratio, the angle has to be in the second quadrant. So when you take the inverse cosine of this decimal here, you'll get 97.7 degrees. And that definitely comes from the second quadrant as we can see, okay? So 97.7 degrees is your answer for number 2. For number 3, we're gonna let arc tangent of 8/3 be equal to some angle theta, which would imply then that the tangent of angle theta better give you 8/3. So then we build a right triangle. Well, if the tangent of theta is 8/3, this is angle theta, these sides must be labeled accordingly, 8 and 3, and then using a Pythagorean relationship, we should get square root of 73 for the hypotenuse length. So therefore, we're really taking the cosine of theta. Well, the cosine of theta then using our built right triangle is the adjacent side length over the hypotenuse. So our answer is 3 over the square root of 73, which is 3 root 73 over 73. Did anybody get that answer for number 3?
Yes.
Oh,
Yes.
congratulations. Awesome. All right. You are a candidate for calculus 2. No, but you will revisit that when you get into trigonometric substitution in calculus 2. Ladies and gentlemen, you have a great day. Have a healthy weekend, and hopefully I'll see you back next week as we are moving through. We'll begin chapter 5, looking at, I believe, identities. We're going to start diving into identities. And I don't want to be the bearer of bad tidings, ladies and gentlemen, but experience has shown me that as soon as we hit identities and trigonometric equations, that's when life starts to get a little bit more difficult, trigonometry. So I'm just kind of warning you, all right? Don't let up on the gas pedal, okay? We still got to get through trig identities, proving them, and also solving trigonometric equations. All righty, have a good weekend. I'll stay on the line for a couple minutes if you have any remaining questions or issues.
Professor,
Yes, go ahead.
I had a couple questions. Can I see problem number 1 again? I just want to double check one of my steps. So big.
Number 1, we're taking the arc sine of negative square root of 2 over 2. That better give us some angle theta, such that if you take the sine of that angle theta, you have to get back negative square root of 2 over 2. Well, the range of the arc sine function is from negative pi halves to pi halves. So our answer has to come from either quadrant 1 or 2. Well, since the sine of this angle is a negative ratio, our answer has to be in the 4th quadrant. Can't be in the 1st quadrant.
I think that's where I messed up.
Yeah.
I have the second one negative.
Yeah, the signs are always a killer in trigonometry. That's why we always have to be conscious of what quadrant we're in, okay? And that's why all students take calculus comes in very handy in remembering the signs of your trig functions in the various quadrants. Did that help out there?
Yes, yeah, it did.
Okay, all right,
And-
Bailey.
My second question though
Yes.
is I'm going up north for my family camp / reunion. And I won't have service up there. Is there any way I can turn the quiz into you by midnight on Sunday?
Yeah, that'll be okay.
Okay, thank you so much.
All righty, no problem. Any other questions?
Nope, that was it.
All right, have a good weekend.
You too. Bye-bye.
All right, enjoy your weekend.
All right, take care.